Hello, welcome to this. Great job. Okay, so yesterday we learned about vectors and we learned this idea called vector resolution. Vector resolution is when you take a vector, v and theta, and find vx and vy. Simple trick, vx is v cosine theta, vy is v sine theta. It might be on the gradient sheet, but you don't need it, it's pretty obvious. Now we're going to learn why we need vectors and what vectors are for. So let's just say I have two vectors. They could be velocities, they could be accelerations or displacements, doesn't really matter. A, B. Two vectors, A and B. The main idea for today, what's A plus B? What's vector A plus vector B? Let's watch another video.
9,997, 9,998, 9,999, 10,000. Where's the X? Supposed to be right here. 10,000 paces east.
Oh, east? I thought you said west.
West? What kind of compass are you reading, lad?
This one, sir.
That's west, Patrick. You're fired again.
Wow, what a great video. Thanks for watching. Okay, so in the video, the people are like, they're following a treasure map. They're trying to find treasure. And they walked like 10,000 paces east. No, they walked 10,000 paces west when they should have walked 10,000 paces or 10,000 meters. A pace is actually pretty close to a meter. So they walked 10,000 or 10 kilometers west instead of 10,000 kilometers east. How do they solve that? If you're supposed to walk 10,000 or 10 kilometers east, but you instead walk 10 kilometers west, well, can you just walk 10 kilometers east and then you'll be the place you're supposed to be? Is that going to work? Of course not, Mr. Lamb. You need to walk 20,000 kilometers east to solve this problem. Oh wow, thanks Daisy, that was really helpful. Yeah. This is going to seem kind of obvious, but people always make this like weird mistake. Let's say you're getting directions. Let's say you're lost, walking down the street, and someone said, oh, you gotta walk 5 blocks north and 2 blocks west or east. Do you walk 5 blocks north and then go back to where you started and then walk 2 blocks west? No, you walk 5 blocks north, you stop, and then from there you walk 2 blocks west. Let's see what that means for these drawings. If I want to draw vector A and vector B, all that matters is the two parts of the vector. The magnitude and the direction. Basically the length of the vector, how long it is, and which way it points. So here's A, here's B. Look at this vector. It's not a translation of A. It's not A slid over. It's not like a copy of A. This is vector A. If two vectors have the same magnitude and same direction, it does not matter where they start and where they end. All that matters is where the end is relative to the start. If I walk 3 blocks north from Grand Central, or 3 blocks north from Bronx Science, or 3 blocks north from City Hall, it's still the same 3 block north vector. They're all the same. It doesn't matter where they start, where they end. If it's 3 blocks and north, it's the same exact vector. So here's A, here's B. That's also A. That's also B. There's another A. There's another B. They're all the same. I need to draw A plus B. So, well, imagine you're following directions. Imagine you have a treasure map. It says walk along vector A and then walk along vector B. I can start here. I'll walk like this. That's vector A. And then I'll walk from there like this. That's vector B. It's easiest to think of this as displacement, but this also works for velocity vectors and any kind of vector too. This is A, this is B. Displacement is where your ending point is from your starting point. This is vector A plus B. This method is known as the head-to-tail method. Vectors are like snakes. You guys know how there are small snakes like garter snakes, and there's big snakes like boa constrictors? Where do big snakes come from? Big snakes come from small snakes. When two small snakes love each other very much, one snake will bite the tail of the other snake. And then the mouth of this snake and the tail of this snake will fuse together and they'll become just one big snake. That's how snakes work. That makes sense to me. That seems right. To add vectors, you take the tail of one vector and add it to B. So I'm going to take B. That's not B. It has the same magnitude, but not the same direction. You take B and you slide it over. Bam. B. B has to have the same magnitude and direction as this B. Once you have that, this head of A and this tail of B, they go away. They fuse together. They just become snake. Now, this vector has one tail and one head. So from the tail to the head, bam, there is vector A plus B. Pretty straightforward. It's great. The head and the tail just go right into each other. It's kind of like, there's lots of examples. It's kind of like the Human Centipede. If you guys ever seen these movies, if you haven't, you can look them up after lunch. The Human Centipede, the end of the first movie is the exact beginning of the second movie. It's not like there's like some 5 years in between where like the Avengers are just hanging out or like hiding from the government or something. That's it picks up right where the first one leaves off. Same as like Lord of the Rings. I think I haven't read the books in like a million years, but I'm pretty sure like the end of the first book, the people are like walking up a hill, and the second book they're still on the same hill. It's just right where the first one, just one leads right into the next one. That's what the Human Centipede is all about. The tail and the head, they kind of fuse together, and you get one vector resultant. So that's vector addition. It makes sense for displacement because you think of it like treasure map. If it says walk 5 meters west and then 7 meters south, you're not going to walk 5 meters west, then go back to your start point. No. 5 meters west, 7 meters south. You have to start here and end here. Walking 5 meters west and 7 meters south is equivalent to this vector right here, which you could find mathematically using knowledge from last unit or last lesson, but you generally don't have to. That's vector addition. So if you did want to add vectors numerically, it would be kind of tough. How do I draw this? Let's say I have, here's vector A, here's vector B. And I want to figure out what's A plus B. Technically with vectors, you got to draw a little hat on the vectors. If you want to mathematically find out A and B, you have to be able to mathematically describe A and B. Let's say A is like, I don't know, like 7 meters at like a 60-degree angle. And then vector B is like 4 meters at like a 20-degree angle. I'm just making up numbers. How can you figure out A and B? These are just examples. We're not really doing all the math. But obviously, will A plus B have a length of 11 meters? What do you think? Will A plus B have a magnitude of 11 meters in this diagram right here? Tell me if It will or not. It will not. It's going to be shorter than 11 meters. A and B are not lined up in the same direction. So to find A and B, you have to do this. That's A. You gotta find this and this. Do you remember what these two are? Hopefully you do. AX and AY. You gotta find this and this. That's BX, BY. Let's call the resultants. Oh, resultant is another term for the sum of vectors. Let's say A plus B is C. If this is true, then C is A plus B. That means CX is AX plus BX. And CY is AY plus BY. So if you wanted to find C, the magnitude of C would be the square root CX squared plus CY squared. And the angle of C would be the inverse tangent of CY over CX. You don't have to do this that much. The main focus of this lesson is knowing how to draw them graphically. Knowing that, I don't know, for some reason when people draw vectors, they always say, there's my vector J. Here's my vector K. And they always say, oh, J plus K, bam, like that. Or maybe, bam, like that. That's no good. Please do not do that. You gotta take one vector, take K, grab the snake, and shove the tail of K into the head of J. Bam. There's vector J plus K. Vectors can have any name, but that's how you add two vectors. This makes sense for displacement, because if you're following directions or something, you just follow one displacement, then you add on another displacement. But it also makes sense for velocities too. Sometimes you have to add velocities because you have two velocities at the same time. And I think we'll come to that later, not right now. So that's pretty much it for vectors. A tiny little addition to this point. What's a letter that exists? Letters that exist. Here's vector R. Here's vector S. They might look like A and B, but that's not really relevant right now. If this is R, what's negative R? If this is S, what's 2S? Well, think of them again, if you're confused by vectors, imagine displacements. Imagine walking along the path of a treasure map. If it says step R is walk 10 meters south, then what's negative R? Or what's the opposite of 10 meters south? You reverse the vector. If this is R pointing up and to the right, negative R down to the left. If step S on the treasure map says you walk 10,000 paces east, and it's 2S would be do it twice. If you walk 10,000 paces east, then another 10,000 paces east, your total displacement vector would be 20,000 paces east. So just draw S and another S. 2S is basically S plus S. So this would be 2S. And what if I wanted 2S minus R? 2S plus a negative R. This is 2S minus R. Practice will hopefully make this a little more straightforward. We are going to use this for some specific problems in the next few units, but that's what vectors are. They're just quantities that have direction. These are just some things we do with them. That hopefully it'll make more sense. Like when we learn about forces, you'll see, oh, when there's two forces in objects, you just find the vector sum of those forces. But now you guys know how to add vectors and how to break them into parts and how to do both together. Some of the problems are basically the same thing, but just much more complicated, much more like tricky stuff, I'll answer your questions. Write them down and please ask me when we come back together. Bye.